We are continuing our discussion on multiple variable regression. And so in our previous video, we talked about how multiple variable regression is where you have more than one predictor or independent variable. And in this particular video, we're going to look at Poisson regression. So in the previous video, we looked at logistic regression, where we're predicting the probability of an event. So we predict that it's a type of penguin. We predict that it is that people buy a product. Here with Poisson regression, we're looking at counts. We could count the number of birds. We could count the number of absences of our employees. So we're creating a model that is counts. So it is a measurement, right? It's interval ratio, but it has to be whole numbers. Okay, so we're integer. And that distinguishes it from linear regression, where we have a measurement where we can have fractions of the whole. So again, interval ratio, but there it doesn't have to be whole numbers. Now, in all three models, logistic regression, Poisson regression, and linear regression, these are all types of generalized linear models, we are assuming no multicollinearity. In our linear regression video, we'll look at testing for multicollinearity. You can also check for multicollinearity by doing a correlation, because multicollinear means correlation between your independent or predictor variables. So, like I forgot to do in our previous video with logistic regression, is to run through just quick here the code here, where we look at the regression between the two predictor variables we started with. And you can see here, using Poisson for our bill length and flipper length, because these are both measurements, they're both ratio data. We would use Poisson, and you can see that they are highly correlated. So one of the reasons that we had this warning here about quasi-separation, and the reason that the two variables weren't both statistically significant, is that they were highly correlated with each other. So they had a multicollinearity issue. All right, we're actually going to be doing Poisson regression, but it has the same assumption. The assumption is that there is no multicollinearity. That is, there is no correlation between the multiple variables you're using to predict, in this case, counts. So for our Poisson regression example, you can work along with us. We are at drstephpowers.github.io/BIA. We are working here in chapter 10 under the regression workbook, so click on that. It will then open up a page that looks like this. Open it in Google Colab, so click on that. You then need to make sure you're logged into your Google Drive and that you have saved a copy so that you can run the code and tweak the code. Okay. All right, I'm going to switch over to this one where I am already logged in. And for this particular example, what we're going to do is we're going to use a data set from Gelman, Fagan, and Kiss from 2007. And this data set looks at New York City Police Department's stop and frisk policy. Okay, and so what we have in this data set is that we have the number of police stops from January 1998 to March 1999. And then we have data that looks at the population. We have information in terms of the number of past arrests, the precinct number, which goes from 1 to 75, the ethnicity of the individual who was stopped, and the type of crime for which they were stopped for. So in this particular data set, the precinct 1 through 75, that one's difficult to deal with because we can't just, there's no meaning to whether your precinct is 2 or 60. And when we have these nominal variables, right, so it's a category, then you have to do what is called one-hot encoding. And with our one-hot encoding, we would turn this into a binary or dichotomous variable where we would say, are you precinct 1? Yes or no. Are you precinct 2? Yes or no? Well, that's a lot of variables, right? So we're going to just ignore the precinct number. In this data set, because it's available for more complex analysis, you could look at, for example, the combination of precinct and some of these other characteristics. So maybe you want to focus on specific precincts that are more likely to do stop and frisk. Okay, so you could focus on specific precincts rather than do every single one. Now, we want to look at and see if the ethnicity of the person being stopped impacts whether or not they're being stopped. And in this case, instead of looking at whether they're being stopped or not, we're looking at the total number of stops. So if we look at an area that has a greater ethnicity of one particular group, are there likely to be more stops or less? And so here, these are counts. So our ethnicity groups are Black, that's label 1, Hispanic 2, and White 3. When you do one-hot encoding, you create all these binary variables, but when you create your model, you can't use all of them. So for example, we could create a new category called Black and have it 1 for Black and 0 for everybody else. We could create a category called Hispanic, 1 for Hispanic, 0 for everybody else, and a category for White, 1 for White, 0 for everybody else. We have 3 variables there. When we create our model, we would not include all 3. You could include 2 of them to see if, for example, being Black changes the number of stops, being Hispanic impacts the number of stops, but you wouldn't include all 3 because if you include all 3, you create multicollinearity. You create a dependency between the 3 variables. And that's because if you are not Black or Hispanic, then in this data set, you are white. And if you're not white or Hispanic, you are Black. So there's a relationship between those variables. If you only include 2 out of the 3, then you've created that separation and you've gotten rid of that multicollinearity. So just remember when you're doing one-hot encoding that you don't put every single variable into your model. Same thing with crime. We have violent for 1, weapons 2, property 3, drug 4. Encode them so they're separate variables. Violent 1 for violence, 0 for everything else. The weapons variable, 1 for weapons, 0 for everything else. And if you build the model, just make sure you don't put all 4 into it. Okay. All right. So how are we going to do this? Well, first we're going to start with our models from sklearn. Just like with the logistic regression video, I'm going to show you the machine learning sklearn models. If your focus is on predicting the number of counts, then this package is what you need. If your focus is on determining how statistically significant the ethnicity of the person being stopped or the reason they're being stopped is on the number of stops, then we don't want to use the sklearn machine learning method. We want to use a statistical package that gives us whether or not each of these variables is statistically significant, and we want to focus on the values of the coefficients in the model. Okay, so we're going to go through those. All right, so from sklearn, linear model, Poisson regression, we're going to use train test split to divide up the data set into data that we can build the model with. That's the training data. We'll withhold 20% to be the testing data. This particular data set is available from Columbia University, so we can call it as a URL. So the URL, and here's the link, and then we need a way to convert it. So we're using pandas. Make sure that you have installed pandas from the very first line of code in this workbook. And we're going to have it convert the information as a CSV. So let's load that in. Okay. And so we could look at the full table here. It's 900 rows, or we could use frisk.head with our parentheses at the end, right? If we did this, frisk.head, we could then, we could see just the first couple rows instead. And remember, you can always tell it how many rows you want to see by putting a number in there. Okay. All right, so let's start our one-hot encoding. So we're going to create a variable called Black. We're going to basically copy over the column that's called ethnicity. So we're going to create a second column called Black. It's going to match the ethnicity column. And we're going to replace where 1 stays as 1 and everything else becomes 0. And it'll give me, when I ran this before, it was nice and clean. But now when I run it, I get a bunch of text and commentary here. That's because they're giving you a warning that they're going to change the way that the replace command works. And so it's just giving you a heads up for a future change. All right, our table is here. We're still good to go. Okay, so this one added Hispanic. I clicked on the wrong one. This one will add Black to our, and then here we have the Hispanic one we just did. you would do that in the other order. So you would have just black here, and then you'd have black and Hispanic in your second one. So I don't need to encode the third category because of that multicollinearity piece. So I could just do black and Hispanic. And then for crime, we could do drugs. So let's have the variable called drug. Anything that's labeled a 4, which is the drug, will get a 1 label. Everything else will be 0. So we're essentially copying over the column that is crime, and then we're replacing the labels with the 1 hot encoding. Okay, so we have our drug column. We could do weapons, copy the column over, replace it. In this case, the label 2 was for weapons, so we did that. You could repeat this if you want to focus on some of the other variables. Just remember that you can't use all 3 or all 4 in your model. So we did drugs and weapons, but you could instead focus on property or violent, add them to your table. Okay, all right, so let's create our model. Test train split, take our big data set, separate it. 20% is the testing data. We are going to use, to start us off, let's see if the person being stopped being black and the stop for drugs, if that changes the number of stops. So here we're kind of testing the stereotype, which is that African Americans are more likely to be stopped and that they're more likely to have a drug charge. So is that shown in the data, right? That's kind of what we hear about the stop and frisk from that period of time. So let's see if that predicts the number of stops. All right, so we're going to take our 2 predictor variables. That's going to go into our X data, 20% for test, 80% for train. We're going to make sure we shuffle the data just in case it has some order to it. Okay. And we are going to predict the number of stops. So let's separate the data first. Then, just like always, call the model, fit the model. So we're going to call the model. We're going to fit the model. Okay. And we could, if our focus here is on prediction, we could then do just like we did with logistic regression. Remember the logistic regression? If I go back, we have this Y-pred. We could do that same thing with our other data set. So I don't know why I didn't put it in here, but it's because the focus really isn't on predicting the number of stops, but I could throw it in. So let's add that. Now, this is not LR. It's the name of my function here, which is Poisson. Gonna do it based on the test data. So I could, for example, run this and you can see, right? It doesn't mean a whole lot to us, but you can see the predicted number of stops. Okay, they range. There's some 47s, 113s. So you can see the predicted data. Our focus here today is going to be on building the model and how statistically significant these variables are in predicting the number of stops. In the machine learning sklearn package, you can use this call here of coefficient and intercept to get the values for your formula. It's going to be applied to whatever you named it. So just like we fit Poisson and we predicted from Poisson, we are going to get the coefficient and intercept from what we named. So we'll pull that information here. Now, how do we interpret it? Well, when it comes to Poisson, the average observed counts is equal to E, exponential here, and then B0, that's your intercept, plus B1 times X1. So if we're going to convert this here, that's 4.73 plus, and then our B1 here is 898. Okay, so 9. X1 plus, and then we have minus 0.87 minus 0.87 X2. Okay. All right, so make that a little bit easier to read. There. Okay, let's try that. Okay, so here's our formula. Now, what does X1 and X2? It's going to be the same order you put them in. So X1 is going to be black, X2 is going to be drugs. Okay, now when we do this, how do we interpret the results? Well, to interpret the results, we are going to have to pull out our calculator just like before. And we got to... It's very similar to kind of the logistic regression in terms of we're going to take these values and we're going to go and use our e to the 4.73. So notice I'm getting different numbers than what's written in. That's because I randomly built the training and testing data. So when you pull different numbers to be in your training data, you're going to get slightly different results. That's why we're looking for statistical significance, because we want to extrapolate beyond just the amount we had pulled from the data set. Because if we pulled a different set of training data, we get different numbers. You want to be able to extrapolate to the greater, in this case, stop and frisk program. What kind of statements can we make about how the number of stops were influenced by things like whether the reason for the stop was listed as being drugs, whether the individual being stopped was an African American. So those types of things we want to look at. Did those impact how many people were stopped? All right, so we want to look at statistical significance. All right, so what do? We pull up our calculator and we clear it out. And then we type in 4.73. That is our intercept here. We're going to do e to the 4.73 and hit equals. And you get 113.3. So 113.3. So the average number of stops is what that intercept gives you. So e to the 4.73 or 113. The average number of stops is 113. All right, now, how does that average change based on the variables that we chose? So we would go and we would look at our 0.898. Okay, and we put that in our calculator. 98 and exponent there and equals, and we get 2.45. So what does this mean? This means that if you are black, you are 2.45 times more likely to be stopped, blacks have 2.45 times more stops than non-blacks. Okay. So we interpret it similar to the logistic regression in terms of we look at it versus the number 1. And here we have 2.45, so 2.45 times or 145% more than those who are not in that category. All right, let's look at the other one, negative 0.87. Negative 0.87. Pull up our calculator. Negative e 0.42. All right, so what we do is we compare 0.42. We compare that to 1. Notice the number's less than 1. So drug crimes are associated with less stops than other types of crimes. How much less? Well, we take 1 minus 0.42, and when we do that, we get 0.68, right? No, what is that? 1 minus 0.42. There we go. 58% less. There. All right. Whoops, don't need that extra text box. So interpreting our Poisson regression, we figure out what our coefficients are, we figure out what our intercept is. E to the intercept will give you the average number, and then you can see the impact of your variables by taking e to those coefficients. If your coefficient is positive, then it increases. If your coefficient is negative, then it decreases the impact. What we don't know from this is whether it is statistically significant. All this is telling us is about the data that we use to build the model. Now, we can predict the values. So there's a line of code. Figured it went somewhere. So you can predict the values, and that gives you this stuff here. Okay. You could look at the accuracy of a Poisson regression. It's a little harder to do than with logistic because we are looking at counts and not just is it a label or not. So to look at the error, how far off the model is, we would take that predicted and we would need to find the error. So the error is the difference between the actual and the predicted. We've seen that before. We're using NumPy to do this subtraction. So this is code you've seen. And in order to do this, we had to first kind of convert the y-test to be NumPy just so it's in the right format for this calculation here. So if you do this, we find here the average error in this particular set is 10. Notice that that error, if the average is 113, then for the most part, the number of stops was off by about 10. And it tells you that the predicted, because remember this is test minus predicted, that the predicted is 10 lower. Okay, it's off by 10. We could plot the error to see what it looks like. So here we can use matplotlib.pyplot as PLT. We're going to just plot the error here. We'll use these other ones. So I'm installing them now. We'll use them later. Right now we just want to plot our error. So we just need this first package. And we're going to plot that error that we just calculated. And then I'm adding here a horizontal line that's on 0 because you want an error that oscillates around 0. Sometimes you should be higher, sometimes you should be lower. If you're too much skewed towards always high or always low, there's a problem with your model. It's not as accurate. So when we plot this, it should look like random scatter around 0. And so we can see there is a bunch of extremes here where we're off quite a bit. So this would tell us we should have some extra variables that can help discern the difference and why these particular data points are so much higher than what we predicted, because we predicted lower numbers. Okay, so to figure out our variables and the impact our variables have, we are going to use our statsmodels.formula.api as SMF. And I've imported it again because I probably forgot that I copied this line of code from somewhere else. And so we're going to import the statsmodel.formula.api. So stats model formula, that's the SMF. Just like with the logistic regression example, we need a data set where the variables we're using to predict are X variables, and the thing we're predicting here, the number of stops, are all in one table. So just like we did before, we were switching before the sklearn to the SMF, we are going to do the same thing. So we're going to use pandas and concatenate. So the X training data and the Y train is all in one table. So we're going to use black and drug to predict the number of stops, and it's all in one table for the SMF package. So we'll call this train 2. We'll output our table here. Okay, you'll notice when I did that, it changed what was showing. That's because each time I run this, because I haven't specified the seed in that test train, I get a different group each time. So you'll get a different one too. All right, so then the setup, just like before with the logistic regression, same kind of layout, which is we are going to call here a Poisson from SMF. We are going to predict stops. You see that squiggly, that tilde, that's to the left of the 1 on your keyboard. And we're going to use black and drug to predict the number of stops. And this is coming from the train 2 data set. We call the model, we fit the model. And then the part we want here is the summary. So when we look at the summary, we're looking at these intercepts and coefficients. And we're looking at, are they statistically significant? So notice that for these, we have black here. This does not span 0. Drug does not span 0. These are all negative. These are all positive. So both variables are statistically significant. Now, what's important to note here is this R squared is quite low, 23%, which means we're missing other variables that explain the variability in the number of stops. So while the variable black and the variable drug are statistically significant, there is other variables that we're missing. Now, we may have collected them in our data, we may not. We may be able to get a better formula, a better algorithm, but we may not have, because we may not have captured the variables that truly help us understand the number of stops beyond the 2 that we have here. Okay, we're doing a pseudo R-squared because, again, R-squared is designed around linear regression and Poisson regression is different. Okay, so the question becomes, can you create a Poisson regression model that better predicts the number of arrests? So can you add in some additional variables so that you can get that R-squared higher? To do that, you're going to have to go back here into our test train data and add some other variables, right? So we could add, for example, weapon. Okay. Now, we could run back through the sklearn, but we don't need it. We can do this separately only in our stats model. Okay, so here we're going to combine it. So you can see now I have weapon added to this list. And so then I'm going to add here, add weapon. But I have to make sure it matches the name of the variable. Okay, run it. When we look at weapon, it is statistically significant. You can see there that does not span 0. The p-value is less than alpha. And so it is an important variable, but notice the R-squared doesn't go up a whole lot, right? It's like 1%. Okay, so we're still missing something that's important to explain the number of stops. But we can see and we can interpret the impact that these different variables have by taking those coefficients, just like we did before, right? And determining how big the impact is. So when we look at this, we know that the impact is statistically significant because our p-value is less than alpha, our 95% confidence doesn't span 0, and then we can go from there to figure out how much of an impact. And for weapons, we would take 0.6489 and e to that, hit equals. And so we can see that a weapon stop increases the number of stops 91%, right? It has a big increase in the number of stops. Okay. If your coefficient is greater than 1, or sorry, if your coefficient is positive, then it will have an increase, and if your coefficient is negative, it will have a decrease. Okay. All right, so try creating other models and see if you can get the R-squared to go up and to see how much impact those variables have. But remember, you can't include all of the binary or one-hot encoded variables from your original variable, because if you include all of them, then you create multicollinearity.